Good morning, everybody. Welcome to the second part of Chapter 5 that we are working on. Moving on with probability. Yesterday we looked at the general addition rule, the little tiny things that we have to look at when events are not disjoint. Today we are looking at what's called conditional probability. And conditional probability is something that we have to use when we don't have independence. And so we'll talk about all of those things as we move ahead here, and what independence really means. But let's just kind of define a few things here first. So first of all, back in chapter 3, we looked at those things called contingency tables. You might remember those when we talked about the Titanic, and it was split by class. It was like first class, second class, third class, and staff. And then it was like living and died, right? And then we had all of the percentages for when they were going to live or die. And we found out that it was probably better to be in first class because if you were staff, you most likely died. Right? And we talked about conditional distributions in that sense, in saying that if you were alive, what's the probability that you were in first class? And like I said, the probability was much higher. If you were a living person that made it through the Titanic, there's a higher probability that you were in first class than if you were in third class or if you were a staff person, because those people were at the bottom of the ship and probably died. Okay? We're going to answer those same types of questions today, only we're going to talk about it in the terms of probability. And when we want the probability of an event from a conditional distribution, meaning a condition has been set, we have this notation that we want to write. Okay, so look at that notation. That's P of B. Okay, but what that means is the probability of B given A. So what's the probability that event B will happen given that we know event A has happened? A probability that does take this condition into account is called conditional probability. The other way that we can kind of maybe write this, excuse me, instead of P given A, what we might say is, if we know A, what is the probability of B? Basically saying, if we have some prior information that event A has happened, whatever it may be, what then, knowing that A has happened, what then is the probability of B happening? And so that's what that represents there. This is a conditional probability. We might also call it a dependent, right? Dependent. That's why it depends is such a funny slide name. We might call it a dependent probability because the B, the overall probability of B given A, depends on what happened in event A. So let's look at some examples of this. We'll get through the formula first. So to find the probability of event B given the event A, we're going to restrict our attention to the outcomes in A, meaning we only really want to look at A. Okay, we want to see what's happening in A. We then find the fraction of those outcomes, B, that also occurred. So that's what this formula here is representing. So the probability of B given A is the same thing as the probability of A and B divided by the probability of A. That is, all of the outcomes in which B occurred as well as A divided by the probability of A. Okay? And notice P of A can't be 0 because if this probability has a 0% chance of happening, then we know that A has occurred. Or excuse me, if it's 0, we can't calculate a probability, which means if this didn't occur, then there's no probability to do something for B, right? It can't be 0 though because we're saying A happened. And because A happened, it has to have a probability bigger than 0. Now let's look at an example of this. The table down below here shows the results of a poll asking U.S. adults whether they were looking forward to the Super Bowl, and whether it was the game, the commercials, or they didn't plan to watch. And you can see that they blocked this by male and female, so that we can see maybe differing results between males and females. So let's just ask some questions about this particular table. There's my information again. So first question, what is the probability of an adult looking forward to the game? So notice that this has nothing to do with whether it's male or female. It just says whether an adult is looking forward to the game. So what are we trying to find here? We're finding the probability of looking forward to the game. P of game. Okay, so where on the table do I see the probability of the people who are looking forward to the game? These are the males looking forward to the game. These are the females looking forward to the game. These are the people looking forward to the game. And we're comparing that with the people who, the total amount of people. So the probability of looking forward to the game is 479 over 1008. And if we really wanted to be super special, we could do that decimal. I'm definitely not walking to my desk to get a calculator to do that. That's why my voice stayed the same sound, the same pitch and volume the same way, right? I'm pretty sure I got away with that. Okay, this is 0.475. So there's a 0.475 chance that an adult is looking forward to the game. Okay, again, stressing notation, right? You want to be able to find this. This is really helpful towards understanding these probabilities, right? P of game, the probability of looking forward to the game. Next question, what is the probability of an adult planning on not watching the game? Okay, so what is this, what would this be? You should pause the video and try to figure that out for yourself before I write it down. So pause it now and then figure it out. Well, if you pause it, I guess you're not hearing this, but anyway. Okay, so what are we looking for? We're looking for the probability of an adult planning on not watching the game. So P of not watching, right? Okay, so let's find P of not watching. Notice that it says an adult. We should change the color. This is all red. You see how that's red? Yeah, that's all red. P of not watching. So where are the people that are not watching? Where are the adults that are not watching? That would be these guys. And we're comparing that to the total. And so this is 292 over 1008, which if you do this on El Calculadora, you end up with I just broke a calculator, 0.289. Oh, good, it's not broken. Notice neither of these are conditional probabilities yet. We haven't done that. We're just looking at this notation. Again, this notation being especially important to be able to figure out because that notation helps so much with being able to use the formulas later. Let's look at a couple more problems. What is the probability of being a male and looking forward to the game? Okay, so notice there's a little bit more to this one. It says being a male, and then it uses the word and, right? That's a key word right there. And looking forward to the game. So what are we looking for here? We're looking for P of male and game. So what's the probability that you are male and you are interested in the game? Well, where are the males that are interested in the game? That would be these people. Those are the only males that are interested in the game. And who are we comparing it against? Are we comparing it against all males? Are we comparing it against all of the game watchers? Or are we comparing it against everybody? In this case, we're comparing it against everybody. This is 279 over 1008, which is 279 divided by 1008, which is 0.277. So the probability of being male and looking forward to the game is 27%, right? Notice the way that this problem is phrased, it's not saying anything about of all people who are watching the game, or of all males, what's the probability? It's saying, what's the probability of being male and looking forward to the game? That's everybody, right? We got to compare that to everybody. So that's why we're comparing to the 1008. Okay, next question. What's the probability of a male looking forward to the game? Okay, so what are we looking for here? What is the probability of a male looking forward to the game? Well, we know that a person is a male, right? That is prior information. What is the probability of a male looking forward to the game? So what we're looking for here, the male is a given condition. What's the probability that there is a male? We know it's a male looking forward to the game. Well, that would be game given male. And so what are those people? Probability of a male looking forward to the game. So we are now looking at only the males, right? We are we're making a condition that a person has to be a male. We're not worrying about females right now, which is really weird for a male. But we're only focusing on the males. We're not looking at the females who are interested in the game. So of the males, there are 279 out of 492 looking or interested in watching the game. And that's 279 over 492, which is a 0.567 chance. Now, I also want to point out that we can use the formula to do this, that same problem. If we use the formula that's given on the previous slide, we have P of game given male. What we would need to find is P of game and male over P of male. Okay, that's the formula that was on a couple slides ago. Well, we know that P of male and game is 0.277. We found that in the previous problem, right? P of male and game, that's 0.277. We need the probability of being male. Well, the probability of being male in this particular set of data would be this out of the total. So that's 492 divided by 1008. That's 0.488-ish. And so if we do that division, hopefully, we should get something very similar to what we got. That is 0.567. Okay. So we can use the formula, in this case with the conditional distribution, or the table, the contingency table, we can do it without. But there's nothing wrong with us using the formula to do that, right? I could find that information. P of male and game, we figured out in the previous one. That was 279 over 1008, 0.277. Probability of being male, that one, we had to figure that out, but the probability of being male is 492 out of 1008. And so 277 over 0.488, 0.567. Okay? So the formula works. But like I said, sometimes we don't need formulas because there is a, intuitive way to solve the problem. Let's look at a couple more problems here. So if you are only watching the Super Bowl because of the commercials, what is the probability you are male? Again, we have a given condition being set here. P of, we're talking about only people watching the Super Bowl because of the commercials. So what's the probability you're male? We're saying, what's the probability of being a male given that you're only watching for the commercials? So P of male given commercials. Well, if I'm only looking at people for commercials, I'm only looking at that row. And what's the probability of being male in that row? It is 81 over 237. And again, we could do the formula for this, right? We could find P of male and commercials over P of commercials, and we could do that, right? But we don't need to because it's kind of intuitive on this one. Let's just one. If you are female, what is the probability you are looking forward to watching the game? Well, we're given a condition. If you are female, that's a condition. So what's the probability you're looking forward to the game? That's P of game given female. And let's use a different color here. The given condition is female, so we're only looking at that column. What's the probability that you're a female who's looking forward to the game? Those are the ones looking forward to the game. Those are all the females. So that's 200 over 516. And we could find out the decimal for that, but I don't feel like it. So there we go. Conditional distributions given a contingency table. We can answer those without the formula. We can answer them with the formula if we want to, but there's a more intuitive way. Let's do one last example where we have to use the formula. Let's go back and look at those campus meal plans information that we did yesterday. So, just to recall your information, 56% of college students live on campus. 62% have a campus meal plan, 42% do both. Boom. While dining in the campus facility open only to students with meal plans, you meet someone interesting, right? We'll put interesting in quotes there, right? Interesting. You know what we mean, interesting. Okay. Anyway, what is the probability that your new acquaintance lives on campus? Because you met this interesting person on campus, in there, you want to, find out if they live near you. This is going to get awkward fast if we keep talking about it. So let's just move on. What's the probability that your new acquaintance lives on campus? Okay. Notation-wise, what does this look like? While dining in the campus facility. So that tells us something. We've been given a condition. We're dining in the campus facility. That means we have a campus meal plan. Okay? So, given that we have a meal plan, what's the probability that we live on campus? Given that we have a meal plan, right, because we met this interesting person while we were dining, what's the probability that we live on campus so we can quickly get to the other person's house? I mean, so that we can know that they live near us. All right, we're going to have to use our formula for this one, right? Formula, P of B given A equals P of B and A over P of A. So in our case, this means what is the probability of having a campus meal plan and, living on campus and having a meal plan over the probability of having a meal plan. And in the information that we're given here, we can figure that out. What's the probability of campus and meal plan? 42% do both. 0.42 divided by, what's the probability of having a meal plan? 0.62. 0.62. So 0.42 divided by 0.62 gives us 0.67. So if you met this interesting person in the campus facility, and then you wanted to find out where they live, because that's not creepy at all, there is a 67% chance that that interesting person you met does live on campus as well. And I think that's kind of all I wanted to talk about today. Oh, it's angry. Well, can I do anything here? Oh, whoa. Maybe. Okay. So, in general, the general multiplication rule here looks like this. That was what we talked about in chapter 14. However, this is only if things are independent. Okay? Things like having a campus meal plan and living on campus, not independent though, right? It could be, so there's a chance here that if being on campus, living on campus, you're more likely to have a meal plan. So we can't guarantee independence on this. So we have to alter our rule to include things when there is dependence. And that rule looks like, I'm going to keep hitting buttons till it shows up. We're almost there. Okay, there it is. That rule is for P of A and B, it equals P of A times P of B given A. So if I take the probability of event A and then I multiply it by the probability of B given that A has happened, we'll get P of A and B. Now, wait a second. Wait just one cotton picking minute, Mr. Dilly. What are you trying to pull? Because if you were to just divide this by P of A, right, and divide this by P of A and just mess with this algebraically, those cancel. Wait, this is just P of B given A equals P of A and B over P of A. This is the formula that you've already taught us. There's nothing new about this. Well, that's true. All we've done is rearranged it, right? The general multiplication rule, the same way that we've defined this conditional probability, is just our general multiplication rule. If you multiply the probability of event A happening times the probability of event B happening, given that A has happened, you get that P of A and B. And that's all I want to say today. Tomorrow we're gonna, whoa, things are still coming up. Tomorrow we're gonna talk about independence, right? What does it actually mean to be independent, and can we look at probabilities and find out if two things are independent? But that's tomorrow. I've got some problems for you to do today. I will see you on Thursday.